Okay, in this video we're going to look at continuity. So before we actually start the video, what I want you to do is to go ahead and write down on your notes, there in front of you, go ahead and write what your definition of continuity is, as far as your knowledge up to date, without reading through the notes, without looking at the notes, without looking anything up online. Don't even try to apply it to math. If you don't want to, that's fine. If you don't know any definitions applied to math and continuity, just give me your definition. So go ahead and pause it, write that definition, and then come back, and then we're going to talk about what it is. Man. So first of all, you have your definition of what to this day, up to this point, what continuity means. So in the terms of math, it's going to mean something very similar to, probably, very similar to what you wrote. The word continuity comes from another word, continuous, and continuous is something that has no breaks in it at all. It can have curves and bends and even sharp curves, sharp bends, whatever, but it can't have any breaks. So basically, if you look here, it says a function whose graph can be sketched in one continuous motion without lifting the pencil is an example of a continuous function. Okay, so I'm guessing that's probably something similar. You wrote something similar. Maybe it's not applied to math or what we're doing here, which is perfectly fine. Let me pull this window up. There we go. So now, continuity at a point. Okay, so now when talking about continuity at a point, there are different types of points. I know it might sound weird, but there are two types of points. There's the interior point. So at a point, what we mean is what we're looking at of a function. Okay, so you have a graph that you're looking at. So there's the interior points of a graph. So if I just really quickly sketch a graph over here. Okay, this is my graph. This is f of x. You have interior points, which are between your start and finish points. So, whoops, on the line, all of these green points, okay, working a little slow here, but all of these green points are your interior points on the graph. All right? So now, if a function is y is equal to f of x, so if f of x is continuous at an interior point C in its domain, the only way that that can be true is if the limit, so if you look right here, come on, pen, right here, the limit as x approaches C of f of x is equal to, so what this means is that the limit is equal to the y value at that point. So if we're looking over here at the graph, sometime today, there we go. Gotta love technology. So if we're looking here at the graph, so let's say this big green point is point C. The y value is the same as the limit. So remember, the limit is as you approach that value from the left and the right. So it's continuous. All right. Now the other one is an endpoint. So there's only at most two endpoints on a single particular function. Now if you have piecewise, it can be different because there are a bunch of functions put together, but ultimately really there's only two endpoints. Okay, so now with an endpoint, the function is continuous at a left endpoint. So let's say this is a. If and only if the limit as x approaches a from the right, so as you're approaching this value from the right, okay, the limit from the right, its one-sided limit, is equal to its y value. And then for the right endpoint, the limit as x approaches b from the left is equal to the y value at that point. So that's what that's saying. So go ahead and just pause the video, take a minute, and write that stuff down so it makes sense to you. Okay, again, this stuff down here, limit as x approaches a from the right, which is basically the right-handed limit, has to be equal to the y value at that point. And here the left-handed limit has to be equal to the y value at that particular point. Okay, so those are the endpoints. It's very important. Endpoints are very important because a lot of the time on the AP exam, they look at not only does the student know everything about what's going on inside, but what if the outside is not continuous? So what if it's not inclusive versus inclusive? Okay, so then down here we're going to have a list of the types of discontinuities. Go to the next page. So first of all, there are removable discontinuities. Removable discontinuity is basically if you have a graph that has a hole. This is a simple removable discontinuity. Now, a lot of times, I should say sometimes, not a lot of times, sometimes a removable discontinuity can have a hole where that hole is plucked out and put somewhere else up and down that little x value there. Right? So this is still a removable discontinuity. And a function of a removable discontinuity can look something like x minus 1 times quantity to x plus 1 all over, let's say, x plus 1. I don't know. And you notice that there are factors in the top and the numerator and the denominator that are the same, and so they can cancel or remove. That way that discontinuity is removed. Second one is a jump discontinuity. And so if you're tracing the graph with a pen or a pencil, jump discontinuity, in order to go from one function to another function, you literally have to pick up your pen or pencil and jump up or down like that. Okay, so now a jump function, a lot of times, probably most times, it's going to be a piecewise function. So for example, you would have y equals x from, let's say, 1 to 3. So it's going to be 1 is less than or equal to x is less than or equal to 3. And then y equals, let's say this is 5. So your second function is y equals 5 from 3, not inclusive, to probably infinity or something. Because if I put this on there, the arrow means it keeps going. Anyway, so then that would be what it would look like algebraically if it's broken. Infinite discontinuities. You've done more of these types of discontinuities than probably any other. These are your asymptotes. So if you have an asymptote, something like this, it goes whoosh, whoosh, something like that. A lot of times this could be like y equals 1 over x plus 1, something like this, where it's not removable, and you can't plug, for example, in this case, you can't plug -1 in here, because if you plug x equals -1, it's 1 over -1 plus 1, which is 0, so 1 over 0. And remember from pre-calculus, that creates, or even algebra 2, that creates a discontinuity, which is an asymptote. And the last one, and the least common, I've never seen it show up on an AP exam, but we're going to just quickly go over it because it's not all that difficult, is an oscillating. It's kind of like a sine wave that just is kind of on drugs when it gets closer and closer and closer to some point. Okay, if you were to take, for example, y is equal to sine of 1 over x, and if you were to take and put a zoom box around, this point and keep zooming in, keep zooming in, keep zooming in, what you would notice is that it oscillates even faster and faster. The more that you zoom in, it oscillates faster and faster. And so what that means is it never flattens out. One side never equals the other side as far as limits go. And ultimately, there's really no value there because it's always going up or down no matter how far you zoom in. And so that's what's called an oscillating discontinuity. So here's an example. Go ahead and try this example on your own. Just try it. Because if you always watch me do the problems, it's not going to be beneficial. Try it on your own, pause the video, then come back, and we'll check the answer together. If you need a hint, I can give you a hint right now. If you don't want a hint, then pause the video and try it. So my hint is try to factor. Factor the top, factor the bottom. Of course, the top is already linear. Okay, it's the first degree, so you can't do that. But go ahead and try to factor the bottom, and let's see what happens. Now go ahead and try it, and then come back and see how you did. Alright, so let's see. The bottom will factor into the quantities x minus 1 and x minus 3. And if you're not sure how to do that, just ask me in class, and I can clarify. And you notice in this case, the x plus 1, x minus 1 do not cancel. And so this is as simplified as it'll get. So what that means is, look, if I plug 1, x equals 1, and x equals 3 into the denominator there, I'll get 0 for both of them. So if I plug 1 in there, it'd be 0 times negative 2, which is 0, so it'd be x plus 1 over 0. If I plug 3 in there, it'd be 2 times 0 underneath 4, and so it's just going to be 4 over 0, which is undefined. So you have these vertical asymptotes going on at x equals 1 and 3. Okay, so those are, remember, the vertical asymptotes. We're going to call those infinite. You can either write out infinite or put the infinity sign, infinite discontinuities. Okay, so there's infinite discontinuities at x equals 1 and x equals 3. So hopefully you were able to define, or actually find that discontinuity and define what it was. In your homework, there's going to be a lot more types of discontinuities that you have to look for, but these are it. The first three are the most popular: removable, jump, or infinite. Remember, if you have a piecewise, you want to look for most commonly, jump and then removable. So if it's a piecewise, it'll either be a jump or removable, or it could be an infinite discontinuity depending on what those functions are in there. If it's so piecewise, and these other ones are easily identified too. So anyway, this is the first part of the video. I'm going to split it in two so it doesn't get too long. On the next video, we're going to take a look more about continuous functions, throw in some composite functions, and the important intermediate value theorem for continuous functions. And also do some problems on one-sided limits, which is a pretty popular AP topic that they like to test you on.